LangGraph state management mechanism employs a reducer pattern to aggregate node outputs into shared state variables, enabling deterministic state transitions through a directed computation graph. This implementation leverages typed state schemas and runtime context injection to model iterative processes with controlled side effects. We will examine how a state graph is configured with a custom reducer function, how nodes interact with the shared state through partial updates, and how the graph is compiled into an executable runtime that processes state transitions. The demonstration will show the initialization of state with annotated reducers, the definition of computation nodes that read and write to this state, and the compilation step that produces a runnable graph instance.
From LangChain core, runnables import runnable config. From typing extensions, import annotated, typed dict. From LangGraph, checkpoint, memory import in-memory saver. From LangGraph, graph import StateGraph. From LangGraph, runtime import runtime. Def reducera, list B, int none list. If B is not none, return a plus B. Return a. Class state type dict. X, annotated list reducer. Class context type dict. R, float. Graph equals state, graph state schema equals state. Context schema equals context. Def node state, state runtime, runtime context dict. R equals runtime, context get R, 1. X equals state, X minus 1. Next value equals X, R asterisk 1X. Return X, next value. Graph add node A. No. Graph set entry point A. Graph set finish point A. Compiled equals graph compile. Step 1 equals compiled, invoke X, 0.5 context equals R, 3. Hash X, 050.75.
This example demonstrates how to build and execute a stateful computation graph using LangGraph's StateGraph. The pattern shows a single-node graph that processes state through a reducer function, with the node performing a logistic map calculation based on context parameters. The StateGraph is configured with a state schema that uses a reducer function to accumulate values in a list, and a context schema that provides runtime parameters. The single node, A, reads the current state value, applies the logistic map formula using the context parameter R, and returns the next value. The graph is compiled into an executable form that implements the runnable interface, allowing invocation with both state and context. This approach is useful for modeling iterative processes where each step depends on both the current state and external parameters. The reducer pattern enables state accumulation without requiring nodes to manage list operations directly. The separation of state and context allows for flexible parameterization of computations while maintaining clean state transitions. The single-node design here is simple, but demonstrates the core pattern that can scale to more complex graphs with multiple nodes and edges. Let's break it down.
From LangChain core, runnables import runnable config.
Imports runnable config from LangChain core. Runnables, which provides configuration options for runnable components in LangChain.
From typing extensions, import annotated, typed dict.
Imports annotated and typed dict from the typing extensions module, which provide type hints for adding metadata to types and defining dictionaries with specific key-value type pairs.
From LangGraph, checkpoint, memory import in-memory saver.
Imports the in-memory saver class from LangGraph's checkpoint memory module, which provides an in-memory checkpointing mechanism for saving and restoring graph execution states during testing or development.
From LangGraph, graph import StateGraph.
Imports the StateGraph class from the LangGraph graph module, which provides a builder for creating state-based graphs where nodes communicate through shared state.
From LangGraph, runtime import runtime.
Imports the runtime class from the LangGraph. Runtime module, providing access to runtime execution capabilities for LangGraph workflows.
Def reducera, list B, int none list.
Defines a function named reducer that takes two parameters, a list and an optional integer b, which can be none. The function returns a list. This appears to be a reducer function signature used in StateGraph to aggregate values from multiple nodes, where the first parameter is the accumulated value and the second is the new value to incorporate.
If b is not none, return a plus b.
Checks if variable b is not none, and if true, returns a new list created by concatenating list A with a single element list containing B. This effectively appends B to O while preserving immutability by creating a new list rather than modifying the original.
Return A.
Returns the value of variable A from the current scope, exiting the function and passing this value back to the caller.
Class state type dict.
Defines a state class that inherits from typed dict, creating a type-hinted dictionary structure for representing state in a stateful computation graph. This establishes a strongly typed schema for the shared state that nodes in a state graph will read from and write to, ensuring type safety and clarity in state management.
Class context type dict.
Defines a context type using typed dict, which creates a dictionary-like structure with type annotations for its keys. This establishes a type-safe context object where each key's value type is explicitly declared, enabling static type checking and IDE support for context data used in the application.
Graph equals state, graph state schema equals state. Context schema equals context.
Creates a StateGraph instance configured with a state schema defined by the state class and a context schema defined by the context class. This initializes a graph structure where nodes will communicate through shared state, with the state and context schemas defining the data structure and context management for the graph's execution.
Def node state, state runtime, runtime context dict.
Defines a function named node that takes two parameters, state of type state and runtime of type runtime context. The function is declared to return a dictionary. This appears to be a node function signature for a LangGraph state graph, where nodes process state and return updates to that state.
R equals runtime, context get R, 1.
Retrieves the value associated with the key R from the runtime context dictionary, defaulting to 1 if the key doesn't exist, and assigns it to the variable R.
X equals state, X minus 1.
Retrieves the last element from the list stored under the key X in the state dictionary and assigns it to the variable X. This assumes State.x is a list-like object that supports indexing with -1 to access the final element.
Next value equals x r asterisk 1x.
Computes the next value in a logistic map sequence by multiplying the current value x by the growth rate r and the remaining capacity, 1x. This formula models population growth, where the growth rate slows as the population approaches the carrying capacity.
Return x, next value.
Returns a dictionary with a single key x mapped to the value of next value. This represents a partial state update where only the x field is being modified, leaving other state fields unchanged. The dictionary format matches the expected return type for StateGraph nodes, which must return a partial state that will be merged into the shared state.
Graph add node A.
Adds a node named A to the state graph, where the node is defined by the variable node. This establishes A as a named component in the graph that can process state and potentially contribute to the graph's execution flow.
Graph set entry point A.
Sets the entry point of the graph to node A, meaning execution will begin at this node when the graph is invoked. This is equivalent to creating an edge from the special start node to node A in the graph structure.
Graph set finish point A.
Marks node A as a finish point in the state graph, causing graph execution to terminate when this node is reached.
Compiled equals graph compile.
Compiles the state graph into an executable graph object and assigns it to the variable compiled. This creates a runnable instance that supports methods like invoke, stream, and other execution operations.
Step 1 equals compiled, invoke x, 0.5 context equals r, 3. Hash x, 0.50.75.
Invokes the compiled graph with input x, 0.5 and context r, 3, producing the output x, 0.75, where the state key x now contains a list of 2 values. The invoke method executes the graph's logic, passing the provided input and context, and returns the resulting state after processing. This implementation showcases LangGraph's reducer pattern for state management in a computation graph. The reducer function aggregates node outputs into shared state variables, enabling deterministic state transitions. Here, the reducer appends new values to a list, while the node function performs a logistic map calculation using both state and context parameters. The separation of state and context allows flexible parameterization while maintaining clean state transitions. The single node design demonstrates the core pattern that scales to more complex graphs, where nodes communicate through shared state and reducers handle aggregation. The compiled graph executes as a runnable instance, processing state transitions through the defined computation flow.
The reducer discards each number, yet the graph collects them all like a magician's endless hat.